Hello and welcome to Calculus 1. Calculus is a study of motion. Calculus is a study of change. We can measure and compute things with calculus, explore, and then eventually build. Calculus is base for physics, physics is base for engineering, and if you have engineering, you make stuff. Now, whether it's biomedical engineering or electrical, mechanical engineering, structural, whatever it is going to have financial engineering as well. It's going to have calculus. For whatever reasons, there is a marketing engineering. I never understood that one, but fine. Calculus pretty much touches every aspect of our life. Everything that we picked up was probably machined by something that touched calculus in one point in time. So calculus is base. And today, we regard calculus as elementary mathematics. It's elementary through all differential equations, actually. And then after that, you have many years of math to catch up with the current levels. Calculus consists of three major topics: limits, derivatives, and integrals. And the chapter 2, which we are going to explore for the first 2 weeks, is chapter on limits. So the first lecture on limits is going to be the lecture on the basic idea of a limit and the actual precise definition, the rigorous definition of the limit is at the end of the chapter, I guess. I don't know why, but such is the way of the book we are using, I guess. So we'll hold off to the precise definition of the limit and just work with limits until we get there. So, what is a limit? Guys, limit is a fancy way to compute the y value. That's the most basic street language you can get to understand what the limit is. So limit is a fancy way to compute y value of the function. That's not a mathematical definition. That is the bottom line that you have to understand. So it's a street talk. Limit is a fancy new way to compute y value of the function. You know from pre-calculus, hopefully, that y is equal to f of x. That you can plug in x value into the function and compute the output value y. So, this is the output of a function. This is the input of the function. So if you have your function y equals x cubed plus 1, you can compute f of 2 by plugging in, and you get 9, because 8 plus 1 is 9. This is your pre-calculus. Input causes output. Definition for a function is function is a rule. This is going to be on your first test as a question. I am telling you right now, this verbatim is a question on a first exam for points, and you either write it or it's a 0. Function is a rule which assigns to each x in the domain a unique y in the range. We underline words rule, domain, range, and the word unique is underlined twice. Let's go. Talk about the functions. In mathematics, a rule would be a formula, just like I have over there. So y equals x cubed plus 1 is a rule. So formula, that's what the rule means. And then domain are all possible values that you can plug in for x. In this case, everything. Positive numbers, negative numbers, real or irrational, rational fractions. You can put whatever you want, right? But there are certain functions where you can't. Square root function does not allow you to put negative numbers. Logarithmic function doesn't allow you to put negative numbers and so on. So there are certain restrictions for some functions. So your domain is the set of all allowed values, right? Technically, whenever there is a party, I'm not in the domain because I just eat everything when I show up. So I'm excluded from the domain of a party. Yes?
There are like rule systems though, like if you have x, you can put in a value that's not going to be like a unique y value. It's going to have like y can be the same sometimes, and those aren't functions, right?
Yes, like circle, sure.
Yeah, so are we ever going to work with them as far as limits is concerned?
No, but we are going to see them later with implicit differentiation, so they will pop up.
Okay.
Calculus deals with functions, and then for the non-function relations, we will have some tools that we can use to deal with them as well. Okay. So we'll see that. Range is the output. Everything that you can get as an answer from this expression. So in this case, 9 is the output. It sits in a range. And now we get to the word unique. The word unique is underlined twice because that is what makes the function. This uniqueness, meaning that for this particular function, number 2 produces 9, and that's the end of the story. Number 2 cannot produce 4 or 7 or negative 1/2. It produces uniquely 9. This is extremely important. Otherwise, we would only have chaos and nothing else. Imagine you're trying to text someone and you want to text, okay, that's it. You're texting 2 letters. Imagine if there was no function correlation between what you type and what shows up. You push all, M prints, because anything can happen. You see that? Yeah, that is uniqueness. You push O shows up. You push K shows up. Not you push O and M shows, and then you push delete, and then R shows, so now you have MR. Right? You see that? So that's what the uniqueness means. There is a rule, and the function guarantees that any time you do this thing, the same thing will happen for everyone for all eternity, everywhere in the galaxy and beyond. Now, very important thing for your career and life is to start relating these things immediately with world around you. So, to do the experiment on functions, I present you the light switch. What is the function of the light switch? Yes?
It turns the lights on and off.
Beautiful. What is the domain of the light switch?
These are 2 positions it could possibly be in. Up switch or down switch.
Okay, well, or the way to excite it. Like, what are all of the things that can excite the switch? Give me an example.
Movement and
Yes. Remember this guy?
the finger.
Yeah, look at that. Boom. So, this, definitely in the domain of the light switch. How about that one?
Technically, yes.
How about his nose?
You want to get
Per ear.
That's a little harder.
Uh-huh. Can you do it? Yeah, you does, right?
You can fix it.
Now, can I extend my arm, pick this up? Can I use that? Car key. Give me an example of something that is not in the domain for me to use to turn the light switch on or off.
It's strawberry.
I can do the strawberry.
Water.
Nothing.
What? Nothing. So nothing is a good example. It's a 0. I can definitely do it with a strawberry. I should bring it next time and I hope I can read it. Does anyone have a strawberry?
You should have asked before I left my house.
Yeah. Oh, you had one of those strawberries that was all white and fuzzy?
No, those cost money. Also, there might be mold there.
No, I said the fuzzy strawberry, you know what I mean, right? Yeah.
Yeah.
Just leave it for like 7 months. It's awesome. I left an apple in my office for 8 months. Well, it was awesome.
Okay.
No, I took the picture, I posted on Instagram, and I put 8-month-old. It was so awesome. You go to the hashtag, and all you get is all these pregnant ladies and babies. So either 8-month-old pregnant or 8-month-old babies, and my apple in the middle. Yeah, you just need to have a right hashtag. Tons of fun. So let me give you an example. Moon. All right? Can't use that to turn the switch on and off. What's the range? What's the output of exciting the switch? Yes, lights are on or lights are off. Great. Now the word unique. You see, the good thing about the function is that the word unique makes sure that anytime you touch that switch with whatever way you can, it always toggles these lights. You don't have to worry about starting your car or causing the major earthquake in Peru or something. No. Unique. Unique. Can you start your car with this switch? Yes. All we need to do is to get the remote starter and then just wire the switch to click that. Fine. Does it turn on the lights? No. Then you change the function, and now the function of that switch is to turn the car on and not the lights. See that? So, sure, by changing the function, you're changing the function of a function. So, function is going to be the central idea of calculus. You take the limit of the function, derivative of the function, integral of the function. If you run into a non-function, like a circle, we will be able to differentiate circle using implicit differentiation, and then you will have to wait for a long time at the end of Calc 2 to integrate circle and do other stuff. And then Calc 3 will be awesome. So 99.5% of the time we will be dealing with functions. And you need to recognize when something is not a function and then critically think if and how you can beat that part. So, x cubed plus 1, it's a function. It passes vertical align test. It goes through 1, it's shifted 1, right? Because it's plus 1 and all that. What's not a function? Circle is not a function. This symbol is not a function, right? Anything that when you do the horizontal line test will cut more than once vertically through the picture. So this is the introductory review of Pre-Calc 1, basics on functions so that we can survive. I said limit is a new fancy way to compute y value of the function. What you have from pre-calc is that calculation you see. You plug in a number, you get the answer, and you move on with your life. Now we are moving into calculus. And the calculus says, what is the limit of x cubed plus 1 as x goes to 2? And the answer is 9. You cannot get a different answer for this type of a function. So limit of x cubed as x goes to 2 is 9. So now what is the difference? First off, if this on top was good enough, why bother with the limit? That should be question number 1. Yes?
So I'm guessing that you use a limit whenever you're talking about motion on the Cartesian coordinate plane.
That's perfect, actually. Yep.
Okay.
You nailed it. So pre-calculus and functions is frozen in time and space. It's a single calculation, input in, input out, and that's it. How would you describe in words when I say x goes to 2? Does it spell standing still? Does it spell frozen in time and space? No. X goes to 2. That means that I have x values that are marching on the x-axis and they're going where? To 2. You know that there is a location on the x-axis that it's marked as 2. And you get to go there. And you get to go there from the left, and you get to go there from the right. Make sense? So, limit is going to compute the same thing that pre-calculus computes. But it's going to compute it through the motion, not through computing a single point. And that gives us certain advantages over the system we know from before. All of your mathematics that it's following is going to be always the upgrade and something more powerful than what you had before. We are constantly making things better and more powerful and more general as you keep going up. So now let's discuss this limit graphically. We are going to draw the graph of x cubed plus 1. So it has to go through number 1. And then what I'm going to do is I'm going to say this is number 9 over here, because we know that 2 gave us 9. So I have my x cubed graph over here. It's x cubed plus 1. It shifted 1 unit up. So the black lines you see going from 2 to 9, those two lines, those two black lines, the horizontal and vertical ones, are your pre-calculus lines. The exact point 2 goes up, hits the function, bounces off, gives the answer 9. That's your pre-calculus. Now where's the calculus? Calculus is going to be in the red and blue lines. as you are walking towards 2, remember the wording is x approaches 2. That means you are literally walking on the x-axis going to position that it's labeled 2. What motion would this produce on the function? It will produce a motion upwards on this function, which as a reflection produces the motion upwards on the y-axis. Do we all see that? So as you walk on x, it produces the upwards walk on function, which produces the upwards walk on this y-axis. Blue approach from the other side. From the right, you are approaching the 2. That means you are going down and you are going down. Hopefully you see that as you squeeze on 2, you squeeze on 9, right? Limits do not compute directly. They say the pattern shows that the answer is going to be 9, right? And we can demonstrate that by using the table of values. So now I'm going to have my x values on top and the y values on the bottom. I'm going to pick 3 values to the left and 3 values to the right. Left values, let's be 10 cents away, and then let's be 1 cent away, and then 1/10 of the cent away. Do you see that these numbers are getting closer to 2? Right? This needs to make sense for everyone in the classroom. It's the basic idea of the limit. So 1.9, and then this is closer to 2, and this is closer still, right? So we are now going to 9 by getting the values that are closer, going to 2 by picking values that are closer and closer to 2. On the other side, if I am 10 cents away, then I am 1 cent away, then I am 1/10 of a cent away. Are we all green on this? I mean blue on this? Good. Now, we can use Abacus to compute all of these values and see what we have. So I'm going to plug each of these values in the function and compute the y's. So 1.9 cubed plus 1 is going to give me 7.859. 1.99 cubed plus 1 is 8.88. 1.999 cubed plus 1 is 8.988. Do we see the trend of numbers rising towards 9? Right? Isn't this one at the end almost 9? So these are marching towards 9. Let's go with the blue. 2.1 cubed plus 1 is 10.261. 2.01 cubed plus 1 is 9.12. 2.001 cubed plus 1 is 9.012. Do we see how these numbers are falling into 9? If it walks like a duck and quacks like a duck, it's a duck. So the answer is 9. This is how limits compute. Very important thing to learn right now, that the limits never compute at the point that you're interested in. You never get to compute at 2. We can compute at infinitely many points around 2. We never compute at 2. What computes at 2? Pre-calc. But pre-calc is limited in that fashion. Because what happens if the function is not defined for point 2? Can you get the answer? No. Would limit get the answer? Yes. Because limit doesn't care that you have an open circle here. Because limit computed all of the values before and all of the values after, and they were all screaming, it's 9! Even though 9 was not there. Now the funny analogy to this is how you fix the bridge whose one segment in the middle collapsed and broke. You approach from one side, you approach from another side, and you just patch it up. Right? Pre-calc can't do it. Pre-calc would have to go from the canyon and it's going to go through the gap and like, see? This is what the difference is. So, what is the purpose of the limit? What does it do? It computes the y value. 9 is the y value. So, don't go with any extra stuff. It's as simple as that. That's what limit does. Computes the y value. Now, it's the fancy new way. You see? You don't compute at the number you're interested in. You compute at the infinity of the numbers around. Now, clearly, pre-calculus doesn't allow for that because you can't sit in pre-calculus and check infinity of the numbers. So calculus computes and then infers what the answer is, right? So that if the function value is missing, we can still get it. So that's what limits do. And believe it or not, the lecture is pretty much over. I call the red and blue approach Romeo and Juliet approach. Yeah. So, right, blue for the boy and red for the girl. Standard. You see, they both approach at 2 and then they meet at 9. But if the function is disconnected, they don't have to meet. If it's a single value missing, sure, they'll meet. But if the function has a jump or something, they are not going to meet. And if they don't meet, we say there is no limit. Let's take a look at that. Say you have a piecewise function, f of x equals to, say, x plus 1 for all x is bigger than 0. And let's say x squared for all x is smaller than 0. So this is f of x equals to. So this is your piecewise function. And you want to know, well, actually let's put equal sign. Where do you want equal sign? Top and the bottom. Top. Okay, fine. It doesn't really matter. We just put the black dot. So, what is the f of 0 and what is the limit of f of x as x goes to 0? Now we're going to learn some differences between pre-calc and calc. Well, we graph first. Remember, no graphing calculators on your exams, so you need to be able to graph this by hand. Plus, you can actually graph this on your calculator anyway. Even if you had the calculator, you'd just be staring at it if you don't know what to do. So, let's go. When you study mathematics, make sure you are studying the words and connect those words to the world around you. What is the meaning of the word piece?
Not whole.
Not whole?
Like there's different parts of it.
Different parts of it? Great. So when I say piecewise function, this means that the function has parts. It's not one thing. And we clearly see that we have two parts over here, two pieces. Therefore, piecewise function. This part over here is the domain on which that part, piece of the function exists. So, the purple x bigger than 0 piece is this side of the graph, because this is where the positive x values are. And the other green part is this side of the graph. So as I am graphing piecewise function, I have to graph x plus 1 in a purple side and x squared in the green side. So graphing x squared in the green side with the open circle at the origin, and I just have a parabola. Right, the entire parabola would look like this, right? This is x squared. But I am not allowed to put the purple side on because x squared doesn't belong in the purple domain. Purple domain has x plus 1, and that is this linear line. So now when I remove all of these, you get your graph. Your x squared belongs to the domain that it's less than 0, the domain that are negative x values, and your linear x plus 1 belongs on the other side. Now we have the graph xy. What is f of 0? Where is the function value for 0?
For calculus, but I don't know how to explain it, would be f of, for 0 would be 1.
1, yes, at 1. It's at 1 because that's what the black dot is, that's what the equal sign is. You see, you get to compute pre-calculus on the line where the input belongs to. 0 can belong here, here, or nowhere. You told me you wanted to belong here. So you will be plugging 0 into this to get the answer. So 0 plus 1 is 1, therefore f of 0 is 1. Right? So it will belong to one of the lines or none of the lines if it's excluded from the domain altogether. Now, what is the limit as x goes to 0 of f of x? Well, we are going to do the Romeo and Juliet approach. So Juliet approaches from the left. She goes down the function into the 0. So limit of f of x as x goes to 0 minus is 0. notation of the minus in the exponent means approach from the left. Juliet. Okay? So, limit f of x equals 0, x approaches 0 minus. Romeo approaches from the right, going down the line, going down the y-axis. Limit x approaches 0 plus of f of x is equal to 1. Are they going to meet? No. We say limit does not exist because they do not match up. They do not end up at the same position. They are apart. Limit does not exist. Limit does not exist because they didn't end up at the same location. Right? You know the story. Two teenagers don't listen to the parents and they die. Beautiful. Right? Listen to people that know stuff, okay? That's simple. Dumb teenagers. Yes?
Where would be like a practical situation where you would use a calculation like this?
Well, a lot of places actually. If you, in certain situations, you need a mathematical way to explain the world around you. The fastest way for me, the quickest example, is the edge of the desk. The edge of the desk over here is not continuous. Because if I approach the desk from this side, my feet are on the floor. If I am to approach the desk from the other side, my feet would be on the desk. That means that when I'm in the edge, I'm going to fall. Where do you use this? To survive. When you're at the edge of the cliff, the limit does not exist. You are going to die if you pass the edge. So it is the mathematical way for us to, let's say, give the mathematical model for a cliff. Now, in engineering, you are going to have a lot of other ideas, and I'm especially going to use that today or tomorrow or next class, electrical engineering, shorting the output. And we'll talk about that as well, and you'll have even more insight into the use of the limit in your own field. So, again, limit is the fancy way to compute y value. That's what it is. That's how simple the thing is as a concept. Now, the way it does it is it computes infinitely many values around the point of interest, and then if the left and right approach match, that's the limit, like they did match in the previous example. If they do not match, the limit does not exist. This idea leads to the most important theorem of chapter 2 that will be dragged along through the rest of the calculus and your educational careers, because limits set up stage for a lot of other stuff. That theorem says this. If the limit of x approaches some number a minus from the left of f of x is the same as the limit as x approaches a plus, which is from the right, and that is equal to some number L, then the overall limit x approaches a, this is from both sides at the same time, is equal to that L. Otherwise, limit does not exist. So this is one of the most important theorems of Calc 1, because the continuity, derivatives, and everything else depends on limits, and this is what gives you limits. You will always be able to compute things using the chart and left and right approach. If you have the most diabolical problem with limits that no one in the math department of MIT can solve using algebra and stuff, you will be able to solve that by using the middle school method. Compute few numbers from the left, compute few numbers from the right, and look at the trend where they're going. The same idea as graphing functions. What is the first method for graphing functions you learn? Pick x's, compute y's, right? Plot the dots and connect them like in a coloring book. That's a middle school level. This is also middle school level. Pick x's, compute y's, and then look at it. Right? It doesn't matter how difficult it is. I can have sines, I can have cosines, I can have e's, I can have functions you have never seen before, like hyperbolic functions, hashtag Calc2. It doesn't matter to you. You can reduce it to the middle school level by picking x's, computing y's, and looking at the trend. And if the numbers from the left and the right match by this theorem, that's the limit. If they don't match, the limit does not exist, and the rest of the chapter is completely irrelevant. This is not efficient. So we have the rest of the chapter. We also use the rest of the chapter to define continuity, asymptotes, and other things. So we need the rest of the chapter. But technically you are done with limits for life with this theorem, because you can always go back to the middle school level, pick x's, compute y's, and look at the trend and say, okay, goes to 9, goes to 9, it's 9, goes to 0, goes to 1, does not exist, because you can't be at home and here at the same time. You can be in the two locations, right? Because that's what this thing is, right? If you regard x-axis as time and y-axis as space, at noon you are home and at RVCC. Really? Right? Limit does not exist. At the same point in time, you are in two different places. Here's another example. Since you asked, when we get to continuity, you will get 5,000 examples for what you asked. But I have to make you happy. Our happiness, your happiness is of our primary concern. Thank you for flying early. Better than United. Right? It beats. Well, at least they didn't throw him out of the plane. I mean, that's you know, it counts for something. A few stitches here. You're okay. Come on, right, man up, right? And now keep the gym. Next time, no one bothers me when I walk in another flight. Just went to the Dominican Republic. So would you like to sit in? There's more space over there. Oh, thank you very much. Try to drag me off the plane, see what happens. Good. So yeah, we're done. This is 2.2. Limits can be found by looking at the graph, and limits can be found by computing the chart. And the theorem says that one-sided limits will decide the fate of the overall limit for the problem. Very important for you to learn the notation, otherwise you are doomed. This minus and plus here are not for decoration. Minus means approach from the left, plus means approach from the right. Now, when I say approach from the right, you are walking to the left because you're coming from the right. Like these things, just sit down and just, radiate a little bit, and it will make sense immediately. So approach from the left minus approach from the right plus, if they match up, the limit exists, and that's that number. If they don't match up, no limit, and that's it. Now, we do have the issue of infinities, which we're going to look later at, and we'll deal with that as well. So infinities are coming up. That's it. So we'll restart for the next lecture, 2.3, algebraic ways to come up with limits. This is graphical and chart or table or chart. So middle school way to get the limit. Now we're going to take a look. We'll upgrade to algebra way in 2.3 to solve the limits. You have a question on this?
I don't know if this is a weird question, but like, how would you, because you say you're determining the point by like how they're approaching each other from one side and the other side, how would you be able to determine, like, it would seem like you would need to do like an infinite amount of calculations if you wanted to determine if it was like 2 or say something like very, very like close to 2, but like infinitesimally smaller, like 2.00001. Like, how would you determine if the limit is 2 or that like smaller thing?
Well, the clean functions are obviously going to have a nice, right?
Okay.
Right? We are going to cover now the more advanced techniques with algebra, which are used because we actually don't want to use the calculations. So the idea is that you have something to fall back on if hell breaks loose, but in general you want to use algebra. And algebra will always spit out the exact ones. So we are going to do a lot of cool stuff here. We're going to subtract infinity minus infinity and get 3/4. So it's going to be beautiful. Try to make that in accounting. That's why they make you take this. Infinity minus infinity equals to 3/4. 75 cents. You got that. Next class.